Good evening. Welcome to day 2 on week 13 of the semester. In the last class, we ended our topics by introducing to you guys how to do different calculations when it comes to molarity. Remember that molarity is going to be a unit that is utilized in order for us to understand the concentration of a particular solution. Molarity specifically looks at the moles of a solute that we have in a particular volume that must be in liters for a solution. You guys need to be able to do a series of calculations when it comes to molarity, including if you're given the grams of a substance to be able to calculate molarity, if you're given the moles of a substance to calculate molarity, or if you are given the concentration and the volume that you want of that substance, you will be able to calculate the grams of solute that are needed. And those are the equations that we pretty much did. Now, continuing on, talking about the topics of chapter 8, the next thing that we need to mention is dilution. Okay? And dilution, pretty much what the process involves is that you're going to have a solution in which a solvent is added to the initial solution. When you dilute and you add more solvent, what you're doing overall is that essentially we are increasing the volume of the solution, and that is decreasing the concentration of the solution. Okay, to give you guys a real life example of a dilution, here we have a can of concentrated juice. These can be usually found in the frozen aisle of any grocery store. Now, we can see here that this one can of orange juice, when you place it in a particular container, in order to get it to the correct concentration, if you don't want to be tasting super sour, depending on what the juice is, or very like concentrated taste, the directions say that you need to add specifically 3 cans of water. So the cans of water is going to be the solvent that we need, okay, in order to create this juice. And overall, since we are not changing, okay, the number of moles of solute, because we already added the first can, all we did was increase the volume because
I just like the message.
Stacey, do you have a question? Nope.
Sorry, I didn't know I was on mute.
Oh, okay. So overall, what we have is that the volume increase in our solution to 4 times from what we started with, okay? Now, when it comes to dilution calculations, understand that dilutions, and in order for us to actually understand what dilutions are doing, we do have an equation. That equation is going to be relating the molarity that we start with to the volume that we start with, and comparing it to the molarity when we have diluted a particular solution to the final volume that we have of that diluted solution. So let's go through the following problem. What is the final concentration when 0.50 liters of a 60 molar HCl solution is diluted to a volume of 1.0 liters? Okay, so whenever we're doing specifically a dilution, understand that our equation is M1 multiplied by V1 equals M2 multiplied by V2. Okay? So we know that for this problem, when it comes to the initial molarity, that's going to be 6.0 molar of HCl when it comes to initial volume, as you can see, is 0.50 liters. Lastly, the final volume is V2. So that is 1.0 liters. And the question is asking, what is my molarity? So we are solving for M2. So in this, you can see that initial molarity times initial volume equals diluted molarity times the final volume of the solution in the diluted solution. So if I'm isolating only the M2 term in this equation, I must divide both sides of the equation by that final volume. So when I do that, the V2 term cancels, and my equations ends up being M2 equals M1 times V1, everything over V2. As you can see on the left side of the slide, we have all the numbers to incorporate them to our equation. So I just plug them in. 6.0 molar multiplied by 0.50 liters divided by 1.0 liters. What is the molarity of that newly diluted solution? So you take 6.0 times 0.5 divided by 1. What is the molarity? Great, 3 molar. But then, based on the numbers that we have, with the correct number of sig figs, what would be the correct way to express it? Will it be 3? Or would it be on another set of digits? Thank you, guys. Exactly. 3.0 molar. Okay. Now, I'm going to do an illustration of how this actually looks like, because I know that when it comes to the assignments for chapter 8, which is due next week. Okay, so next week they have due chapter 8, which already is available to you guys, and then the lab that I posted this week, which it comes with the lab kit. So make sure that you check that on the class Canvas site. So when it comes to this, I want to illustrate how this actually looks like in terms of a container. Let's say that I have a large graduated cylinder. And this large graduated cylinder goes up to 1.0 liters. Okay. Let me do some markings here. 1 halfway, that's 0.50 liters. So we can illustrate this. So if I utilize random colors to represent these solutions, understand that this volume of the 6 molar HCl would fit right here in my container. Now, based on the problem, as you can see, that half a liter volume of 6.0 molar HCl was diluted up to the 1 liter line. So that means that we added a solvent, which, looking at the properties of HCl, this can be water, and we're going to study that more in detail in chapter 9. So as you can see here, in order to make this 1 liter solution, we added in 0.50 liters, okay? So in this question, we were just trying to find the final concentration. But I want to make you guys aware that sometimes when it comes to the questions and dilutions, we need to read carefully the questions. Because at times when you are doing calculations, you need to be aware of what the question is actually asking. And the reason why I bring it up is because in the homework, there is a question on how much water is added for basically taking this concentrated solution to a diluted solution. And because the question asks how much water is added, okay? C2 is not the amount of water added. So let me just write a note here for you guys. So if you ever have to calculate V2, V2 is not the amount of solvent added. V2 is simply the final volume of the solution. So if I ask you guys a particular, in addition to what you guys have to do, a particular question, when I say, how much water was added to make the solution, what would be the answer to that? Put it in the chat. How much water did we add? Exactly, half a liter. Great job, you guys. 0.50 liters. Because we started with half a liter, our final volume, which was already given to us, is 1 liter. So that means that we only need to add half a liter, okay? In order to get that liter that was stated in the problem. Let me see if on my end, I can show you guys the question in the homework. So when you guys look at it, you won't be surprised by, oh, wait, why did I get that wrong? Let me go on my end. Assignment, chapter quiz. Preview. Oh. Let me share. So you guys see the question that I'm talking about. Put a 1 in the chat if you guys can see my browser with the chapter 8 quiz. Awesome. So this is the question that I am mentioning to you guys. Notice that the question is asking, how many milliliters of water should be added to 50.0 milliliters of a 15.0 molar H2SO4 solution to give a final concentration, okay, of 0.300 molar, okay? So that is the question. So let me walk you guys through the following problem. Let me take an image of it so we can have it. and then we can walk through the problem together. Give me a moment until I connect my iPad back. Put a 2 in the chat if now you guys can see at least a snapshot of the problem. Just want to make sure that we're on the same page. Excellent. So when it comes to this problem, okay, observe that what it's asking is how many milliliters of water should be added. Okay. The only information that the problem is giving you overall is your V1, your M1, and your M2. Okay. So step number 1 is going to be the calculation of V2. Okay. So since we know that our equation is M1 times V1 equals M2 times V2, if I divide both sides by M2, the V2 term will be by itself, and the equation overall looks like M1 times V1 divided by M2 is what that final volume is. Again, M1, V1, and M2 are given in the problem. M1 is 15.0 molar. V1 is 50.0 milliliters. Everything divided by 0.300 molar. Okay, so if we round our answer to 368, let's put on the chat, what will be the answer for the V2 term? I think you're missing a 0, Vanessa. But thank you for the other students that actually placed the answer. So when you actually plug this into your calculator and you say 15 times 50, so 15 times 50, and I divide that by 0.3, I get 2,500. And at times students say like, oh, I'm done. I calculated V2 because V2 is the amount of water that should be added. Let me do an illustration like we did before. Remember that the V2 term is not the water added. V2 is the final volume of the diluted solution. So if I illustrate what's happening overall, and let me just do the drawing of my graduated cylinder. This graduated cylinder, again, this is all relative. If this is 2,500, let's say that this is 2,000. Say that this is 1,500. Let's say that this is 1,000. This is 500. Let's say that all the way down here is 50. Okay. Again, this is all relative. This is in milliliters. The way that we illustrate this is by saying, okay, these 50 milliliters of the 15.0 sulfuric acid is right here. What the problem is stating is that we needed to add some water to get a final concentration of 0.3. So we didn't add 2,500 milliliters of water. What we added was up to the line of 2,500. We already had 50 in there. And when we add all of this water up to 2,500, now the solution overall, all of this, has a concentration of 0.300 molar. So then, let's answer the question that was asked. How many milliliters were added? Is the answer 2,500? Great job, you guys. It's not 2,500. As you guys just put it in the chat, what we added. So if the question asks in a future exam, or as you can see, question 7 in your quiz, because it's asking how many milliliters of water should be added. For this type of question, you're going to do V2 minus V1. So the answer of 2,450 that was placed on the chat comes from the idea that V2 is 2,500. And when I subtract that from V1, which is 50 milliliters, then the answer is 2,450 milliliters. Okay. Put a 1 in the chat if now the way that this question is worded, and when we broke it down here by doing the drawing, it makes more sense. I just want to make sure that that little statement of how much water is added does not trip you. If the question would have said, what is the final volume of the solution? Then your answer indeed is 2,500. But because the question is asking how many milliliters of water should be added, then that is variation, because I'm not only interested in the final volume, I'm interested in actually how much water was added. Okay, so I hope that that helps whoever is here in the class or watching the video afterwards. Great. Let's actually do at least one dilution problem. Okay, so I'm going to give you guys a couple of minutes and let's do this dilution question. The question reads, if 30.0 milliliters of a 12.0 molar HCl stock solution were diluted to a volume of 500 decimal place milliliters, what is the molarity of the diluted solution? So I'm going to give you guys a couple of minutes. Let's find the molarity of the new solution. Okay, let's get started with this problem. When we go through the information that has been given to us in the problem, we can see that overall we have C1. We are given M1, and we are given C2. Okay, put a 2 in the chat if you could identify those 3 things in our problem. But just make sure there's 11 people here. And make sure that everybody is following through. Okay, I get 3 people that are following, 4, 5. Anybody else out there want to put a 2 in the chat? I just want to make sure that everybody's following. Thank you, guys. So taking this into account, because I'm trying to calculate, okay, the new molarity. After I diluted it, I'm going to use my equation M1 times V1 equals M2 times V2. Here, I'm solving for M2, so when I rearrange my equation, M2 is going to equal M1 times V1, everything divided by V2. I put in all my information into my equation, 30.0 milliliters times 12.0 molar divided by 500 decimal place milliliters. The milliliters are going to cancel. What is the new molarity if I round it to 3 significant figures? Excellent job, you guys. 0.720 molar of HCl, which is the chemical that we are talking about. Any questions on dilution equations? Excellent. There is one more topic that we need to cover when it comes to chapter 8, and that is osmosis and diffusion. Okay? So when it comes to osmosis and diffusion, sometimes people use them interchangeably, but I want you guys to understand that osmosis and diffusion are going to be related to one another, but they are not the same term. Okay? So let's get started with osmosis. Okay? So osmosis specifically is the movement, okay, of solvent molecules from the region of lower concentration to a region of higher concentration. But the important thing is that during osmosis, there needs to be a barrier. And that barrier is going to be called a semi-permeable membrane. So whenever we're talking about osmosis, we need that semi-permeable membrane in our system, okay? Now, the classic chemical that we just envision that is particularly undergoing this process of osmosis is water. So since water is the solvent that is most common in living systems, at times, many biologists and chemists define osmosis as the diffusion of water across a selective permeable membrane. And we can see in our example that we have in our figure, give it a moment because it didn't zoom in. Let me stop sharing and reshare it. It froze on my side, so give me a moment. Okay, now it's back. So when we look at a system that is undergoing osmosis, okay, you can actually see in this process that, first of all, we have that semi-permeable membrane. In this container, we have that semi-permeable membrane as a barrier, okay? And even though we have equal volumes of our solvent on both sides of that barrier, we can notice that in this example, we have sugar molecules at a different amount on the left side of the container versus the right side of the container. So during the process of osmosis, as you can see, overall, we have the movement of water molecules from the place that has more water but less sugar molecules to a place where we have more sugar molecules, okay? Now, in the process of osmosis, as you can see, we are just moving our solvent from lower concentration to higher concentration, because in this movement of water, then in this case, thinking that water is going to be our solvent, what we are accomplishing overall is that in essence, in this osmosis system, we are diluting the region, okay, that has a higher concentration of solute, okay? So in osmosis, this is what's happening. In the process of accomplishing this, because the volume is being reduced on the compartment on the left, but increased in the compartment of the right, we are concentrating the solution on the left while we are diluting on the right. And overall, we're just trying to find an equilibrium in which both sides have relatively similar concentrations of volume to the number of molecules that we have. Now, diffusion is a process, okay, that specifically has the movement of molecules happening under a concentration gradient. So overall, understand that diffusion is just movement of molecules under a concentration gradient, okay? Diffusion specifically is going to help the movement of substances in and out of cells. To give you guys an example of diffusion, that maybe some of you are like me and love desserts. Let's say that you at home baked a chocolate cake, okay? So it has that distinct smell of, just imagine a fresh baked good, right? Now, through the process of diffusion, okay, you know that gas particles that are detecting, you know, that sweet, delicious treat is going to diffuse in the air, enter through your nose, and you're like, oh yes, I'm about to have dessert. Hey, we're going into Thanksgiving. So who's with me next week? pumpkin cheesecake or pumpkin pie. I'm a sweet potato person, so sweet potato pie. What? Isaiah, you're saying you like yes, ew, or what's going on? You don't like any of that? Oh, okay. I'm just checking. I'm like, what? You don't like it? Oh my God. I know this is the season. I'm not, and I'm sorry, I'm not a big like pumpkin spice latte type person, but I don't know, like that whole thing of like pumpkin spice latte, like people love it. For me, it's more the dessert. I love sweet potato pie. I love pumpkin pie. I love pumpkin cheesecake. Yes, Katie, I agree. Extra whipped cream on everything. Now, for me personally, I'm allergic to milk. It's not the lactose, actually the proteins in milk I cannot have. So if you're with me, you cannot consume milk, go to your favorite Sprouts and on the freezer section, go and get you a Daiya, D-A-I-Y-A. That's the brand. Pumpkin cheesecake. They have regular cheesecake. They have key lime pie. They have chocolate cheesecake. It is a gluten-free vegan cheesecake. You will not know the difference. I agree with you, Isaiah. Pumpkin pie is super delicious. And for example, tonight is Sunset Market. There is a stand that there's this gentleman that actually sells sweet potato goods. He has sweet potato bread, sweet potato cakes. He has sweet potato pie. So good. I don't know. Put a one in the chat secretly. Nobody's going to know other than the people that watch this video again. Who loves Sunset Market? Put a one in the chat if you heard about it or if you've gone. It's so good, right? They have so many choices. I'm going to confess, I love the French fries, the Belgian fry stand, love it. That's one of the places that I go. The other place that I go is Homeboy that has the lemonades. And if that line is too big, I go to the people that are next to the pupusas that also have the lemonades, but they also have like mojitos and stuff. That one, my favorite. You can put in the chat, what's your favorite stand at the Sunset Market? I feel you guys. Maybe one day, even though we're online and we haven't seen each other face to face, I can see you guys. Oh. We have another 30 minutes and then we can all head there because it's open until 9. Oh, maybe we should have like office hours there one day. I don't know, one Thursday. Oh, yes, the barbecue. I agree with Isaiah. My son loves the giant pizzas. Has anybody tried the giant pizzas? So good. He loves it. Like the pizzas are super, the slices, one slice will be enough for the child. But anyways, going back to the fusion. So through the process of diffusion, those sweet smells of those chocolate cakes is how you can detect that a baked good is being made at home. Now, diffusion, to be honest with you guys, it is very relevant in biological systems because many molecules through the process of diffusion are going to move molecules from a concentration, a higher concentration to a lower concentration inside of the cell, okay? As you can see, liquids can undergo diffusion, gases can undergo diffusion too. Now, one of the applications of the diffusion process is illustrated here, which is the process of dialysis. So in hemodialysis, this is going to be for patients that actually the regular filtration systems of the body are not working so well. So for example, the kidneys are actually not able to eliminate all those toxins. So the toxins actually are going to be retained in the blood. So at some point when people are having kidney issues, or kidney disorders, they may require dialysis, okay? So the image that you have on the left is actually illustrating a patient undergoing dialysis. Overall, in the process of dialysis, it starts here. Where the blood of the patient is actually in the machine, extracted from the body. Again, the patient is not going to add anesthesia or something. They just sit down for hours in order for the process to continue. Depending on your condition, you may have to do it several times during the week. So the blood actually goes, okay, from the body into the machine, and there is a pump. And understand that there's going to be in the machine a specifically a compartment that has a dialyzing solution. In this dialyzing solution that you can see that the blood is going to go through this dialyzing coil, what's happening overall is that through diffusion, those toxins that are already in the blood are going to diffuse out into the solution because they are in higher concentration in the blood. So they're going into lower concentration in the dialyzing solution. And then when it comes out, is going to be the dialyzed blood that enters the patient. And again, these concentrated particle or molecules, I should say, that are being extracted from the patient, as you can see, include urea and other waste products that specifically a person that has a kidney condition may not be able to secrete from the body. So as you can see, the process of osmosis and diffusion, they are similar in the sense that there is a movement of particles, but understand that they are going to be completely different in terms of what's happening overall. And this is the end of chapter 8. So the next chapter that we're going to talk about is chapter 9. And in chapter 9, we are now going to focus on specifically acids, bases, and buffers. So let's first start by defining what is an acid and what is a base, okay? So let's get started with the descriptions of acids and bases. So acids are going to be a series of compounds that if you utilize a colorimetric instrument that is called litmus paper, okay, specifically blue litmus paper, if you have to place it into an acid, it will turn red. Acid tastes sour. So whenever you are eating limes or lemons, that sourness is because there's acids present. It is known that acids react with metal and it corrodes them. And in general, the main thing that we know that acids do is that they have positive hydrogen ions, which these H pluses we actually call protons. And acids actually like to donate them. Bases, on the other hand, instead of using a blue litmus paper for a base, we actually utilize a red litmus paper. And red litmus paper, when you put it in a solution that has a base, is going to turn blue. Bases, on the other hand, taste bitter. Bases are described, many of them, the majority of them, by having an OH group. And as you can see, an OH group is called a hydroxide ion. Now, bases feel slippery when we touch them. So for example, hand soaps, drain cleaners, although drain cleaners you shouldn't be putting in your hands, but for example, laundry detergents, those typically are bases. And if you have ever touched these compounds, you know that they feel slippery, okay? Now, we actually have to be really careful with bases. For example, drain cleaners, the reason why I said, you shouldn't touch them is because they are caustic. And caustic means that they are going to irritate skin. Okay. Now, when it comes to the definition for acids and bases, in chemistry, we have 3 different theories to define what is an acid and what is a base. Let's understand that for the purposes of Chemistry 112, even though we have it here, I just wanted to introduce it for any student that has to take other chemistry courses. We don't see examples of the Lewis theory in Chemistry 112. But it's important to discuss what that Lewis theory is. So we're not going to see examples. Now, let's get started with the 3 different theories, starting with Arrhenius. Svante Arrhenius was the first person that hypothesized or came up with a theory that made a distinction between acids and bases. According to Arrhenius' theory, acids are substances that contain hydrogen. Bases are substances that contain hydroxyl. So if you can see here, HCl, because it contains hydrogen, is an acid, okay? NaOH, because it contains OH, hydroxide, that is a base. Now, further experimentation actually allowed us to know that not all bases actually have OH. So a brand new definition needed to be put forward in order to be encompassing or more of the reality of acids and bases. So then Bronsted and Lowry, which is what we have in the middle, came up with a different theory to define acids and bases. There was a message that maybe, can you guys hear me okay? Because it said that the internet was unstable. I don't know if I got choppy in the middle. Can you guys hear me okay? Okay. Okay, no problem. So Bronsted and Lowry came up with a definition that gave us a more generalized definition for acids and bases. And then whenever you're taking like biology courses or in many chemical systems, the most common use definition for acids and bases is going to be Bronsted and Lowry. In the Bronsted and Lowry definition for acids and bases, it says that an acid is going to be donating a proton. And remember that protons is another word for H+. Then a base is going to be always a proton acceptor. Okay. Now, here we have examples of things that act as acids and bases. So for example, ammonia, which is the first compound that we see here, we see it acting as a base in many instances. We're going to see later in this chapter that water is a very interesting molecule because it can act as an acid and it can also act as a base. Okay, it depends on what is the molecule that is paired with. And whenever we have a molecule that can act as an acid and act as a base, we have a particular term to define them. And a molecule that can be acting as an acid and as a base, that is known as an amphoteric molecule. So any molecule that can do both jobs, act as an acid and act as a base, that is known as amphoteric. So even though we don't see examples of Lewis theory in this course, understand that the definition that Lewis came up with for acids and bases, instead of focusing in protons or hydroxides or the transfer of protons, as we saw in the Bronsted-Lowry definition, the Lewis theory basically focuses on the electrons, okay? Since acids are going to donate a proton, okay, understand that overall they are known as electron pair acceptors, and bases are going to be electron pair donors. But again, in this course, we are not going to see examples of the Lewis theory. We are going to focus for the most part on specifically Bronsted-Lowry definition for acids and bases. Now, in section 9.2, we have the definition of strong acids and strong bases, okay? And in the following table, you guys have a sample on the left side, so the table that you see here, of a list of acids, okay? Let me specify to you guys that when it comes to this, I need you guys to know for the next exam. So have this slide available. You should know what are the 6 strong acids. Give me one moment. So when it comes to this list, it's important that you guys know the 6 strong acids. As you can see, HI, HBr, HClO4, HCl, H2SO4, and HNO3. You can see their names on the left side. Those are your 6 strong acids, where the one that is, even though it's strong, is going to be less strong than the one above it, where HI is the strongest strong acid, and HNO3 is going to be still a strong acid, but it's less strong than any of the members that are above it. The reason why it's important to know these is because anything that is not in that top 6 places is going to be a weak acid. So you don't even have to question, a weak acid? Well, if it's not HI, HBr, HClO4, HCl, H2SO4, or HNO3, then it is a weak acid. And this is going to be very particularly important when we talk about buffers later in this chapter. Now, when it comes to strong bases, understand that strong bases are going to be formed by metals of group 1A or 2A in the periodic table, and those cations from 1A and 2A are going to be paired with hydroxide. So when it comes to 1A, remember that this includes the following elements. We have lithium, sodium, potassium, rubidium, cesium. The members of 2A that if they're paired with hydroxide make a strong base include magnesium, calcium, strontium, barium. So again, any of these cations, you see them with hydroxide, then we are talking about a strong base. Now, it is important that since we know what is a strong acid and what is a strong base, where do these names actually come from? Well, the naming of the acids comes from specifically determining if you have a binary acid versus an oxy acid. And binary acids are going to be specifically when you have a nonmetal, okay, that starts with hydrogen. So out of the binary acids, the ones that you guys have to be familiar with is going to be specifically H2S, H2SE, HF, HCl, HBr, HI. Those are the binary acids. How do we name binary acids? You can see here that we're going to utilize the prefix hydro. Then you're going to use the stem of the name of the nonmetal that we have in our acid, and the end is going to be ic acid. You can see in the example that HCl, which we have here in the list, this is hydrochloric acid, okay? Let me name the other binary acids. H2S is hydrosulfuric acid. H2SE is hydroselenic acid. HF, hydrofluoric acid. HBr, hydrobromic acid. And lastly, HI, hydroiodic acid, okay? And these are your binary acids. As you can see here, among my binary acids, the last three are strong acids, HCl, HBr, HI. Now, there is one more acid that, even though it's not binary, is named like a binary acid. So there's an exception to the rule, like many times we've seen in chemistry. So note, remember that HCN, even though it is a hydrogen before, or sorry, a polyatomic ion that has a hydrogen, this is named like the binary acid. So HCN is actually called hydrocyanic acid. Okay, so that is the only acid that has a polyatomic that has the word hydro in front of it, HCN. Then we have the oxy acids. And when it comes to the oxy acids, these are going to be formed by a hydrogen ion and a polyatomic ion. And all we have to do whenever we have an oxy acid is that we have to recall that information about polyatomic ions. I know it's been a while, but we need to bring it back. And if your polyatomic ion used to end with an ATE, when you write the name of the acid that corresponds to that specific polyatomic ion, we're going to take away the ATE and we're going to replace it with ic acid. If your polyatomic ion used to end with an ITE, then what you're going to do is replace the ITE with O's acid. Notice that the oxy acids do not have the word hydro in front of their name, okay? So in order for us to just practice some of these, here I have some chemical formulas, okay? And we're going to name those acids, and we can have the name of some acids, and we can actually write their chemical formula. So let's first go from chemical formula to name. Here we have HNO3, okay? So going back to our knowledge, okay, of polyatomic ions, you guys make sure that you review that. You should recognize that NO3 is a polyatomic ion. What is the name of NO3? Let's put it in the chat. What is NO3? What is its name? Excellent job, you guys. Great to put it in the chat. Nitrate. Now, this oxyacid, because NO3 is present in it, then that means that the name of the acid is going to be, I take away the ATE and I put ic acid. So the name of this acid is nitric acid. We already seen the name of HCl and HI. This is hydrochloric acid. Number 5, that is hydroiodic acid. Let me just write a note here. Understand that chloric acid has the chemical formula HClO3. So hydrochloric acid and chloric acid are not the same thing. Okay. Now, let's look at the next one. HClO2. ClO2 is my polyatomic ion. Let's put it in the chat. What is the name for ClO2? What is the name of that polyatomic? Thank you, Katie. Yes, chlorite. So since it's chlorite, the name of the acid that is formed from hydrogen being now in the presence of chlorite, or the chemical formula for the acid that is derived from chlorite, this is going to be chlorous acid. Okay. Let's do one more. H3PO4. What is the name for PO4? What is the name of that polyatomic ion? Thank you, Vanessa and Dominique. Yes, phosphate. Now, understand that phosphate and also the ones that are sulfur derived, we are not going to just take the ATE, because for the phosphorus one, the stem of that name is going to be phosphor. So for number 4, instead of suggesting that this will be phosphoric acid, the correct name is going to be phosphoric acid. We have the same issue if we have H2SO4. H2SO4, this is sulfate. So instead of saying, oh wait, that's sulfuric acid, this is sulfuric acid. And it just has to do that phosphate and sulfur have different stems compared to the rest of them. So just consider, phosphate, phosphide. So the acid that comes from phosphide, which is H3PO3, that's going to be phosphoric acid. Let me just write it here so you guys have it. So if you have H3PO3, this acid, this is phosphorus. acid. If you have H2SO3, which is the one that comes from sulfide, this is sulfurous acid. So these exceptions to the rules is basically for the phosphates and the sulfates, okay? Excellent. So we have already done hydrofluoroic acid. What is the chemical formula for number 9? Let's put it in the chat. Chemical formula for number 9. Great job, HF. Sulfuric acid, I just did. That's H2SO4. What about carbonic acid, you guys? So what is carbonate? Because if we know that it is an ic acid, then basically this came from H plus mixing with carbonate, which is CO3, 2 negative. What would be the chemical formula for that? Remember that this is when we have to go back into, oh, the 2 that is in the charge is going to be the subscript in the next atom. So what would be the chemical formula for carbonic acid? You guys can take a guess. Thank you, Atasia. Yes. H2CO3. Okay. We have hydrobromic acid. What is the chemical formula for hydrobromic acid? Hydrobromic acid. Thank you, Katie. Yes. HBr. What about hypochlorous acid? This comes from H plus and ClO -1. What would be the chemical formula for hypochlorous acid? Great job. Thank you, Dominique and Vanessa. HClO. So when it comes to these, just make sure that you're familiar with going from name to chemical formula to name for many of these acids. And I only have 1 minute, so I just wanted to mention to you guys, remember that the majority of the bases have hydroxides. And because the hydroxides are going to be with elements that live in 1A and 2A, those are representative elements. So all you have to know is that for naming bases, you need to know that the name of the metal is the first word, the second word is hydroxide. There's only 2 bases that are actually weak bases that do not contain hydroxides, and those are NH3 and PH3. NH3, that is ammonia. PH3 is phosphine. These are the only 2 that are not going to have hydroxides, and because they don't have hydroxides, again, they're weak bases. So this is all for today. Remember, you guys,